In example 6, we want to determine the following integrals. Okay, so these ones are, again, we saw one like this on that first integration page, anti-differentiation page. If I think about this one, sometimes people write the dx on top just for convenience. It's the same thing as seeing this as the integral of 2 over x dx. Doesn't matter where that dx is. You can put it on top of a fraction if you have a fraction. That's actually more common if the numerator is 1. Than instead of having nothing in the numerator or just 1 in the numerator, you stick your dx in the numerator. So just something to think about. Knowing that it can go up there, that's okay. Or off to the side. Off to the side sometimes makes us feel more comfortable because we have our like end brackets of our integration, so we know where it's at, but it can be on the top as well. Okay. And so what are we thinking when we look at, or what do we need to be thinking when we look at 2 over x there? I do need to be thinking about that as 2 times 1 over x dx, because I can't treat x to the negative 1 power as a power function, because that would have a 0 power divided by 0. It's not going to work. I have to see this as 1 over x, knowing that the derivative of natural log is 1 over x, so I can get the antiderivative of 1 over x being natural log. Okay? So again, that's number 9 down here. I know that the derivative of natural log is 1 over x, so anytime I have 1 over x, I have to go back to the natural log. And again, it's written in the form right here of dx over x, because 1 over x is dx over x. Okay? So I go back here and I get 2 times the natural log of x plus c. The other note about natural log is, what? Off the screen, thank you. The other note about natural log of x is this really is natural log of the absolute value of x. It is, even right there. It's just my absolute value symbols are invisible right now. They're there. I meant them to be there, but I'm also just assuming that I'm working on positive x's. We don't often write them just for shorthand, but we assume that we know we're not going to plug a negative into that. Okay, so it's technically supposed to be there, and it's lazy of us not to write them, but you know, we're lazy anyway, so we don't always write them. Okay, but they're technically really supposed to be there. Okay, and then part B. We know that the derivative of e to the pi x would be e to the pi x times pi. So the antiderivative instead of times pi has to be divided by pi. So this has to be e to the pi x divided by pi plus c. And again, you can see that rule down here. It's again just helping us undo the implicit chain rule right there. Now notice that we're only able to do chain rule when we're chaining a constant, or it's a constant multiple that we have. If it's not a constant function, we're going to have a whole lot of issues undoing that chain rule. We have to work on that. There's lots of rules for that. But we can do it for a constant. So if I had e to the x squared up here, you would be like, I have no idea what its antiderivative is, because we don't at this time. But for that constant pi x, it's multiplied by pi, we can just divide by pi, and we've got our solution. Okay, so again, here's some more indefinite integrals. We talked about that one. Oh, we had those special ones, right, where you could do not e to the x, but b to the x times natural log of b, so divide by natural log of b if you're integrating. And then we have our arc trigs. We already mentioned the arctan one on one of those previous pages. You can see what arcsine and arcsecant would need to look like. They look messier to begin with. Anytime you see those square roots in the denominator, you're thinking one of those arc trigs, one of those arcsines, arcsecants, right? So you're looking for your square roots in the bottom there. Okay. Now, we've seen 12 different rules. There are more than 100 special rules of indefinite integrals. There's a link you can type in to get to integration tables. They're also in the textbook. If you go to my math lab and click the textbook link, you can see there are hundreds of rules for special integrands. When we did derivatives, there were 24. And then we're like, yeah, we can do all the rest once we have these 24, right? In most cases, if you think about multiplication and division, you could probably agree, especially if you get into long division, that the opposite, division's a harder thing to do, right? If you think about exponential functions and logarithms were a harder thing to do, right? It's the same thing with differentiation and integration. The opposite process, integration, is in general a harder thing to do than differentiation. So there are more special rules, and there are going to be a lot more special processes. We're going to touch integration, but Calc 2 is all about integration. You spend almost an entire semester learning how to integrate things, because there are lots of special processes, lots of special rules for certain cases. Yeah. Looking forward to that, right? Next semester, you're like, okay, you gotta do some more integration. I just got into integration. What else can I do with integration? So maybe we'll see in a little bit some functions that we won't be able to integrate. Go ahead.
Is that when we'll know like cycloids and histochrom?
No. Unfortunately, you'll have to go on a little further for that. Okay. Okay. Initial value problems. Okay, I'm going to pause real quick.